Hi, my name is Timothy Atwell, and you're tuning in to the Division of Education, Innovation and Energy e-learning program. Today we're dealing with mathematics, and we're dealing with one of the most fun mathematics topics, circle geometry. So, before we begin, we must understand that there are some prerequisites to being able to harness this topic properly. The first thing that we must be able to do is basic arithmetic. We must be able to add, subtract, multiply, and divide. Another thing that we must be able to do, or one thing that we must know all types of triangles. Now, we should know that a triangle is a three-sided shape. And we should know already that there are equilateral triangles, which means that all three sides are the same length. And as a result, all the interior angles are the same measure. We should know about isosceles triangles already. We should know about right-angled triangles already, and so on and so forth. We should also know about the sum of the interior angles of shapes. So for a triangle, we should know that the sum of the interior angles should add up to how much? 180 degrees. And for a quadrilateral, be it a square, a rectangle, a kite, a rhombus, the sum of the interior angles must add up to 360 degrees. Another thing that we must know the relationships when it comes to basic angles. We should know what is meant by vertically opposite angles. We should know what is meant by corresponding angles, alternate angles, supplementary angles, and complementary angles, etc. So, just to recap, some of the things that you may not remember, we may see them as we go forward, and I will try and give a little explanation, but let's move forward and let's try to touch on what is more important at this time. So when it comes to circle geometry, there are some objectives that we must know and we must remember. The first thing about circle geometry that we must know is what is a circle. If you don't know what a circle is, then you can't do this topic. So we must know the circle and the various parts of the circle. We must know the theorem involved in this circle. And then we must also be able to apply these theorems to solving for missing angles as we go forward in this topic. You ready? Let me go. So what is a circle? A circle is a two-dimensional shape where all of the points along its boundary, called the circumference, are equidistant from the center of the circle. Again, a circle is a two-dimensional shape. That means that it is flat. And all of the points on the boundary of the circle, also called the circumference. So if we have a circle here, let's pretend it's a circle, right? If we have a circle here, then all the points on this boundary are equidistant or equal distance or from the center of the circle. Cool? Nice. So now let's look at the various parts of the circle and what they mean. So when we say the center of the circle, we mean the center of the circle. The center of the circle is that point that is equidistant from all the points on the circumference. So if we have a circle here, again, we're pretending it's a proper circle for now. The center of the circle is that point in the middle of the circle that is equal distance from any point of the circumference. So if I was to take a line and go from here to there, that distance would be the same as if I was to take a line and go from here to there. But what is that line? This line that goes from the center of the circle to the circumference of the circle is called the radius. The radius is that line segment, part of the line, that goes from the center of the circle to the circumference or the boundary of the circle. Now, if we have a chord, the chord is that line segment that goes from one point on the circumference to another point on the circumference. And remember, what is the circumference? The circumference is the boundary of the circle. So if we have a circle here, I'm just drawing a different circle on this side. Again, we're pretending it's a proper circle. If I have a line segment going from one point on the circumference to another point on the circumference, a straight line that is, then that line is going to be called a chord. Now, there's a special type of chord that we must know. This special chord is called a diameter. And a diameter is a chord that passes through the center of a circle. What is a chord again? The chord is that line segment that will go from a point on the circumference to another point on the circumference. But if it happens to pass through the center of the circle, let's pretend it passes through the center of the circle for now, then this line is going to be known as the diameter. Now, a tangent is the line that only touches a circle at one point. So if we have a circle, let's pretend we have a circle now. Pretending for now, we'll see the actual circles in a bit, don't worry. But right now, we're just pretending together. So let's say we have a circle. A tangent is a line that is only going to touch the circle at one point. Now that means that a tangent could never pass through a circle. This can never be a tangent, because once it passes through a circle, it's going to cut it at 2 points. A tangent must be outside the circle and must be in such a way that it only crosses at 1 point. That's a tangent. Now, when it comes to an arc is a portion of the circumference of a circle. A portion, a big word for some, or we can say that an arc is simply a part of the circumference. And since we already know that the circumference is the boundary of the circle, an arc will simply be a part of that. So this would be an arc, because it is a part of the circumference of the circle. Great. Now, there are two parts of a circle that are also important that we need to know. A sector is a part of a circle enclosed between two radii. Now, radii is the plural of radius. So if you have one radius, you will have two radii. So a sector is the part of a circle enclosed by two radii and their intercepted arc. So let's say we have a next pretty diagram here. Again, we're just pretending for now. We'll see the actual diagrams in a bit. So let's say we have our circle, and we have our center, and we have one radius here, and we have one radius here. Then the region between two radii and the arc is known as a sector. So here we have a minor sector, which is the smaller sector, but here is also a region between two radii and an arc. So we have a minor sector, and we also have a major sector. Now, when it comes to segment, it's a bit different. So while sector is between two radii and an arc, a segment is between a chord and an arc. So again, we're drawing our pretend circles for now. A circle. And if we have a chord, which goes again from the circumference to the circumference, then here we'll have one segment, which is a minor segment, because it is a smaller segment. Or we can have the major segment, which will be the larger segment. Now let's see if you can see all of these diagrams. Now, here we have our actual circles with actual centers labeled O. They are properly drawn. So it means then that any line that goes from the center to the circumference will be a radius. So here we have a radius. Here we also have a radius. Here we also have a radius. But so it labeled diameter. Hey, you're observant. So, but watch it. The diameter, we said, goes from circumference to circumference and passes through the center. So we should see that the diameter is actually made from two radii. Here we have the chord going from circumference to circumference, And again, the diameter is just a special chord because it goes through the center of the circle. And over here, we have the tangent because it only touches the circle at one point. Here, we have segments because this is a chord. So up here, we have the minor segment because it's smaller. And down here, we have the major segment because it's larger. And over here, we have the sector. If it's between two radii and the minor arc, it's called the minor sector. And if it's between two radii and the major arc, it's called the major sector. Great. So now it's time to look at the 8 rules when it comes to circle theorem. Now, I need you, before we even begin to look at the rules, to remember that there is no order in which the rules are learnt. So it means that when it comes to giving a reason, you can't say, well, circle theorem 3 says that this is supposed to be the answer, because nobody has a clue what you mean by circle theorem 3. You need to know the rules themselves, not what number the rules are. So now let's go. The first rule that we want to look at today is this one, that angles subtended by the same chord in the same segment at the circumference are equal. Let us see if you can watch this video to determine what this is all about. So when it comes to this rule, it says that the angles subtended by the same chord within the same segment at the circumference are equal. So every single angle subtended by the same chord within the same segment at the circumference are equal. And what does that mean? So let's take it step by step. Same chord. By definition, what's the chord? Well, the chord is simply a line that goes from one point of the circumference to the next. So we're going to let our blue line be our chord. And now, if we were to join these 2 points, if we were to draw 2 more lines so that these points join at any point along the circumference, we're saying that the angles are all going to be the same. So here we see that from this chord, the angle subtended, or the angle made by joining the 2 ends, is 69.6 degrees. And if we were to move this, regardless of where we were to move this within the same segment, the angle will remain at 69.6 degrees. So changing, once the chord does not change, this angle remains the same. Now, what about if we carried it this way, where we realize that our angle changed? But I thought you just said the angle will remain the same. Well, what happened? You see, here is one segment. Up here is a different segment. So here, anywhere in this segment, you realize that the angle remains the same. But anywhere in this segment, the angle here would remain the same. Now, what do we notice about these 2 values? Well, 69.6 plus 110.4 is actually equal to 180 degrees. So if we know the angle in one segment, we automatically know the angle in the next segment, because the 2 of them together will be supplementary. Again, let's try a different angle. And we change the angle by changing the chord. So if we make the chord smaller, we're going to make the angle subtended smaller. If we make the chord larger, we're going to make the angle subtended larger. So let's use this one, 51.2. Anywhere along here, it's going to be 51.2. But once we come across here, how much should it be? Well, 180 take away 51.2 should be 128.8. And it is 128.8 degrees. So that is the rule. Any angle subtended by the same chord in the same segment at the circumference are equal. So let's practice this rule. Again, the rule is any angle subtended by the same chord at the circumference within the same segment is going to remain the same. So here they ask us to find the angle angles marked with letters. And in this example, we only have one angle marked with a letter, and that's the angle A. When it comes to circle theorem, it's always good to start with what you know and go to what you don't know as yet. So we know that this angle is 35 degrees. Now the question is, what chord is subtending, or what chord is creating this angle? Well, to determine that, we have to trace back the lines. Let us go back to see where does this line come from. Where this line comes from, this point right here. And the other line comes from this point right here. Now, even though you do not see it, the chord that is making this angle is this. So whether the chord is actually drawn or not actually there, we can simply draw it in so that we can apply our rules. So now we have that this chord is creating this angle, 35 degrees. Now, what do we know about A? What chord is creating A? Well, if we trace it back, we realize that the same chord is actually creating A. And what does the rule say? All angles subtended by the same chord in the same segment at the circumference are equal. So seeing that 35 and A are both subtended by this same chord, they are both on the circumference and they are both within the same segment, it means that A will be equal to 35 degrees. Good? Good. What about the next rule? The next rule that we want to look at is this one, where the angle subtended by a diameter at the circumference is always going to be 90 degrees. Let's look at the video at this time. The angle subtended by a diameter at the circumference is going to be a right angle, or 90 degrees. So what we have to remember is that the diameter is a special chord. It is a chord that passes through the center of the circle. So the angle subtended at the circumference by a diameter is always going to be 90 degrees. Regardless of what side it's on, the angle is going to be 90 degrees. Let's practice now. So here we're asked to find the missing angles, and we have 4 angles. We have A, we have B, we have C, and we have D. It begins to look a bit confusing, but let's break it down into the shapes that we know. Here, so when it comes to A, what chord is subtending angle A? A is formed from point S and point Q. And this line is a chord, but it's a very special chord because it passes through the center of the circle. So that means that this is a diameter. And what does the rule say? Any angle subtended by the diameter at the circumference is going to be equal to 90 degrees. So because A is subtended from this diameter, it means that A will be equal to 90 degrees. Now let's look at B. Where is B? B is down here. Again, let us make sure that we know where this angle is coming from. This angle is coming from the chord SQ. But SQ is the diameter. And if the rule, as we just said, is that any angle subtended by the diameter at the circumference is 90 degrees, it means that B is also 90 degrees. And now we begin to apply some of the previous knowledge that we had before. Because we now need to find C and we need to find D. But where is C? C is here. How can we find C? Well, do we know what shape is this? If we go from P to Q, Q to S, and then S to P, you're right, it's a triangle. But more specifically, because A is 90 degrees, it's a right angle triangle. And the sum of the interior angles in a triangle is equal to 180 degrees. So if here is 90, and here is 40, It means that this plot must be 90 plus 40 is 130. Then we have 180. Take away 130, which is 50 degrees. Similarly, here is 90. And this SQR is also a right angle triangle. So if here is 90 and here is 70, it means that D must be equal to 20 degrees for the sum of the interior angles to be 180 degrees. If you don't believe me, I want you to try and work it out for yourself. See that the answer is going to be 20 degrees. But let's move on. The third theorem that we want to look at today says that the angle subtended by a chord at the center is twice the angle subtended by the same chord at the circumference. Let's see if we can get some explanation from this video. So this rule says that the angle subtended at the center is going to be twice the angle subtended at the circumference from the same chord. So if we have a chord, and again we're using our blue line as a chord, if we have our chord, then the angle subtended at the center is going to be double the angle subtended at the circumference. So if we were to move the angle subtended at the circumference, it doesn't matter because we already know that angles subtended within the same segment are equal by the same chord at the circumference. So if we were to move it, it doesn't matter. And once we know that the angle subtended at the circumference is going to be half of the angle subtended at the center. Or if you rather say it, the angle subtended at the center is going to be twice the angle subtended at the circumference. So let's change the chord, and we see that the rule remains the same. So here we have 144.6 at the center, and a half of 144.6 is 72.3. The angle subtended at the center is going to be twice the angle subtended at the circumference. Now, what is important here, and I want to mention it one time, look at where the angles are. If we look at this shape, so if we focus solely on this shape, so let's see if I can remove this line. Great. So let's focus simply on this shape. This angle is the external angle of this shape, whereas this angle is the internal angle of the shape. So when it comes to the rule, it's important to realize that the angle subtended by the chord at the center, we are measuring the angle on the outside of the shape. And then that angle on the outside will be equal to double the angle on the inside. So that if we were to bring this over here, you realize that, well, these are not 107.7 is not a half of 144.6. However, this is the angle on the inside, which means that we should be measuring the angle on the outside. Now, the angle on the outside will be 360 minus 144.6, which is 215.4. And if we were to halve 215.4, we will get our 107.7. The rule didn't change, but we must remember which angles we are measuring. So, the angle at the center is going to be twice the angle at the circumference, where the angle at the circumference is inside, whilst the angle at the center is outside. So if we were to just draw back our chord, it's in black, but that's all right. Then when it comes to this side, if we're measuring, this is our chord, the angle subtended at the center, we want to measure the outside angle. so that we'll be able to get the inside relationship. Great. So let's practice. And we'll take a simple example to start off. So here we're asked to find the angles at C and the angle at D. Again, we have to start with what we know. So we want to find C, and C is coming from the chord that goes from this point to that point. And again, even though it's not there, no biggie, we can simply just draw it in to help us visualize it. The angle subtended at the center is twice the angle subtended by the circumference once they are both subtended by the same chord. So because 70 is subtended at the center by this chord I've drawn in blue, and C is subtended at the circumference by that same chord I drew in blue, it means that C is going to be 1/2 of 70, or 70 divided by 2, which is 35 degrees. Similarly, because C and D are both subtended at the circumference in the same segment by the same chord, then we know C and D are both equal. So if C is 35, then D is also 35 degrees. Here we begin to see how our rules are coming together. And it's important, again, to remember that sometimes you can have a question that may have all the rules involved. You need to be able to see which rule you want to apply at which time. Also, I want to tell you now that we could have applied the same rule again. Because since D is subtended by this chord, it means that D will be 1/2 of 70, which is same 35. So one person may use one rule, you may use a different rule. It doesn't matter once the rule applies. And I want you to remember that. Now let's move on. What about Theorem 4? Well, Theorem 4 is all about cyclic quadrilaterals. And let's see what this is about. So when it comes to cyclic quadrilaterals, the rule states that opposite angles in a cyclic quadrilateral add up to 180 degrees, or opposite angles in a cyclic quadrilateral are supplementary. So here we have a cyclic quadrilateral. A cyclic quadrilateral, again, means that each point of the quadrilateral is going to be on the circumference of the same circle. So if we have 1 point, 2, 3, 4, all of these must be on the circumference of the same circle. And once that is true, then the angles that are opposite each other are going to be supplementary. So if we just look at this particular shape, 86.1 plus 93.9 is equal to 180 degrees. 93.4 plus 86.6 is equal to 180 degrees. And regardless of where we were to draw them, it will remain the same. Now, do you all see that I'm moving this point, but this angle is not changing? Only the other two angles are changing? Now, why is that? Well, even though you may not see it, if we were to draw the chord that connected these two, then we would realize that this is an application, then we would realize that this is an application of the rule where we said that angles in the same segment subtended by the same chord at the circumference are equal. So even though we're moving this value, this angle is not going to change its value because it is in the same segment. Similarly, this angle is not going to change its value because it's in the same segment. It's a cool thing that we should be able to realize. So just by changing this one, we're not changing its value. And similarly, if we were to change this one, then we realize that this value isn't changing, but the other two are. Because if we were to take this as our segment instead, then we have the application of the rule that angles in the same segment subtended at the circumference are equal. So again, the rule says that opposite angles in a cyclic quadrilateral are supplementary. But I do not want you to just think of it as one rule. See all of the rules beginning to combine. And that way, when it comes to complicated shapes within circles, we'll be able to see what rule we could possibly apply to get the answer that we are looking for. So let's look at this example. Here, they're asking us to find the missing angles A and B. And we have a cyclic quadrilateral. And how do we know it's a cyclic quadrilateral? Because all 4 points of this quadrilateral are on the circumference of the same circle. Which means then that these two are going to be supplementary, and these two are going to be supplementary. So it means that 110 plus angle B will be equal to 180 degrees. And thus, to find angle B, it will simply be 180 degrees take away 110, which we know is 70 degrees. Similarly, to find angle A plus 80 degrees will be equal to 180 degrees. So that means angle A will be 180 take away 80, which is 100 degrees. Cyclic quadrilaterals are fun. I actually like them. They're probably one of the easier ones when it comes to circle theorem.